Welcome to the next video in the series on condensed matter theory. In this video, or actually in the next set of videos, I want to talk about relativistic effects and the importance of relativistic effects in solids. And in this video I will start with the Dirac equation and derive what the relativistic corrections that we need to the Schroedinger equation actually are. In 1926, Schrödinger derived the Schrödinger equation, or actually he proposed the Schrödinger equation. You can't really derive this, and that was a huge success in explaining the non-relativistic quantum mechanical physics that we had at that time. He was able to explain a lot of the atomic spectra with this equation, and it was therefore very quickly accepted and adopted. He introduced a wave function to describe the microstate of a system. So instead of describing a system by the position and momentum of all particles, we now have a wave function. He replaced the energy by an operator with the derivative of time of that wave function, and the kinetic and potential energy are given in the Hamiltonian that acts on that wave function. And the Hamiltonian is given by minus h bar square over 2m. And then the second derivative with respect to positions plus the potential energy. So we have here the kinetic energy and the potential energy. In the first sentence of his paper that he introduced in 1926, which has the name Quantisierung als Eigenwertsproblem. So if you speak German, it is really a nice paper to read. He states that he looks at the simple case of the non-relativistic hydrogen atom. And we know from letters that he tried hard to find a relativistic solution, but he did not really get the hang of that. In 1928, so within 2 years, Dirac then proposed a relativistic equation, and also that was an immediate success and immediately accepted, because he was able to explain a few discrepancies that we have in the Schrödinger equation. First of all, it was well known that all states that we have according to the Schrödinger equation are double there in the experiment. Which is commonly known as the spin, and also at that time the spin angular momenta of the electron. The 1s shell, you can fill it with 2 electrons. You have hydrogen and helium with 1 and 2 electrons in the 1s shell, and only then you go to lithium with 1 electron in the 2s shell. So each quantum state can be occupied only by 1 electron. If you do spectroscopy and you make an excitation, for example from the 3p into the 4s shell, then you would expect that this is given by a single line. And indeed, without a magnetic field, you find that it is a single line. But within a magnetic field, these lines split into doublets, known as the Zeeman effect. And also there you see that each quantum state that you have according to the Schrödinger equation is double there with an effective angular momentum of spin 1/2. And that was introduced by Goudsmit and Uhlenbach, the spin angular momenta, and of course both Pauli and Darwin made this really into a common accepted theory where you now have a spin of 1/2. So Dirac tried to make the Schrödinger equation relativistic. We know that the equation is not Lorentz invariant, so he tried to make a Lorentz invariant form of the Schrödinger equation, and at the same time wanted to solve the problem of the spin doubling of all our quantum states and see if you find a solution for that. So the idea that Dirac had is to have a look at the energy-momentum relations, both classically and then relativistically, and see what kind of substitutions one makes. So classically we know that the energy is given as a half mp square, and if we now want to arrive at the Schrodinger equation, we have to replace the energy by the operator, that is the time derivative, the momentum by the gradient, so a spatial derivative of our states, and the microstate that is given classically by the position and momenta will be replaced by a wave function of position and time. And for one particle I use phi, for many particles I use normally psi. And we then have the Schrodinger equation that gives you the energy-momentum relation by just replacing the energy by the energy operator, the momenta by the momenta operator, and having these operators act on a wave function. Now, we can do the same thing from the relativistic energy-momenta relations. And for the relativistic energy-momentum relations, we know that E square is c squared p square plus m square c to the fourth. At rest, we have E is mc square. When you have a finite velocity, we get an E square is c square p square plus m square c to the fourth. Now let's make the same substitutions. And what we find is that the energy square, I becomes a minus h bar, and then the second time derivative acting on our wave function is equal to minus c square h bar square, second derivative in the spatial coordinates, m square c to the fourth times the wave function. This is the Klein-Gordon equation. And the Klein-Gordon equation does not include spin. And the Klein-Gordon equation has negative energy solutions. We can already see that for the energy-momentum relation that we wrote down, E square is equal to a positive number, which means that E can be both positive or negative. And Dirac wasn't happy with these negative energy solutions. So he tried to find a solution where you no longer have negative energy solutions and where spin naturally occurs within the equation. The fun part is that in the end he did find an equation where spin naturally occurs, and because this describes things like spin-orbit coupling and corrections on the energy levels when you have spin as well as the g factor of the electron, it was immediately accepted. But you still have negative energy solutions, and they correspond to the antiparticle of the electron, the positron. But Dirac wanted to get rid of the negative energy solutions, and he said, well, classically we find that energy is linear, or your equation is linear in energy. Relativistically it became quadratic in energy, and of course when you're quadratic, then a negative energy solution is allowed. So let's see if we can find an equation that is linear in energy. And for that we're going to write E is the speed of light, alpha I pi plus alpha 4 mc square. and we choose alpha I, such that E square is C, I is 1, 2, 3, alpha I pi plus alpha 4 mc squared squared, so that's just the square of what we had before, is m square c to the fourth plus c square p square. For this to hold, we must have that alpha I alpha j plus alpha j alpha I is 2 delta ij. So can we find numbers for which this equation holds? And it's not so easy to check that when alpha should be a complex number, there is no such solution. When alpha are numbers, things just commute, and this is never going to be fulfilled. Now, alpha I not necessarily has to be a complex number. What happens when we make alpha I a matrix? And Dirac's first idea was to make alpha I a 2 by 2 complex matrix. If alpha I is a 2 by 2 complex matrix, then our wave function should be a vector of length 2. Now a vector of length 2 is really nice because that would immediately double the number of states that you have and then give rise to what we now call spin up and spin down. So this immediately, naturally includes then spin into your equations. Now, what could the alpha i's be? And when we think of spin and matrices in spin, then we can have a look at the Pauli matrices, and indeed the Pauli matrices fulfill this condition. So sigma 1 or sigma x is 1s on the off diagonal, sigma 2 is sigma y, is the antisymmetric Hermitian complex matrix with I on the off diagonal, and sigma 3 is sigma z, is the diagonal matrix with a 1 and a minus 1. And indeed, these Pauli matrices fulfill that sigma I sigma j plus sigma j sigma I is 2 delta ij times the identity matrix. So when we make alphas 2 by 2 matrices, we can fulfill this condition. But there's one problem. There are only 3 Pauli matrices. And we need 4 of them because we have also the plus mc squared with an alpha 4 in front. That has to fulfill this relation. We have 4 elements in our 4 by 4, 2 by 2 matrices, which means we can make 4 independent Hermitian matrices. We have 3 of them. The 4th of them is the identity matrix. So there is not a 4th matrix that we can pick that fulfills these conditions. So how did Dirac continue? Well, we saw that with complex numbers we had no chance. With complex 2 by 2 matrices we got pretty far. We also immediately find a natural way to include spin into your wave function or your Dirac equation. So that's nice. So we do the Schroedinger equation such that it becomes the Dirac equation. Let's just enhance the dimension. Let's use 4x4 matrices. And now, of course, we can choose 4 matrices that fulfill these conditions. Alpha 1. Let's just pick the Pauli matrices for that. Sigma 1, sigma 1, but now 2 of them. And the same for alpha 2. On the diagonal, we make 2x2 zero matrices. Minus II, 0 minus II. And alpha 3, we're going to use sigma 3 for that. In alpha 4, we can now pick a diagonal matrix with +1 in the first block and -1 in the second block. And we now have 4 matrices that fulfill the condition that we needed to have, that the sigma I sigma j plus sigma j sigma I is 2 delta ij. If we now write down our equation, then we have IH bar ddt acting on the wave function is equal to C sum I is 1 to 3 alpha I times the impulse plus alpha 4 mc square phi rt. And of course we can put in the momentum operator as well. Minus IH bar C sum I is 1 to 3 alpha I, the spatial derivative, plus alpha 4 mc square times the wave function, where the alphas are 4x4 matrices and our wave function is given by a vector of length 4, where we have spin up, and we will call the first one the large component of the wave function, and then spin down times the large component of the wave function, spin up times the small component of the wave function, and spin down times the small component of the wave function. So we have both spin up and spin down for the large component, and spin up and spin down for the small component. And if you now apply this wave function to something like the hydrogen atom, you will immediately get the correct G factor for your electrons of 2. You will get spin orbit coupling that you find relativistically, and additional corrections that people at that time already could measure. So that's why this equation was accepted as the right equation for the relativistic motion of electrons. You see that we now have 4 solutions instead of 1. So in the Schrodinger equation you have only one wave function to describe both spin up and spin down. We now have 4 components in our wave function. At rest they correspond to the electron with spin up, electron with spin down, positron with spin up and positron with spin down. But when particles move, these are just 4 basis states that you can use to describe the electron with spin up and down and the positron with spin up and spin down. So So we will refer to the large and small components of the wave function. And we'll come back to an example where we take an electron as a free moving particle to see how they mix. And we'll go to the non-relativistic limit of this equation to see what the correction terms are that you find. We'll find 3 correction terms, but that is something for later. For now, thank you very much. Stay healthy. We see each other later.